Hi, I'm Roos. Thanks for joining us today on our paper, How I Met Your Bias, Investigating Bias Amplification in Diffusion Models. Diffusion models have achieved state-of-the-art performance across multiple generative tasks, including image inpainting and unconditional and conditional image and video synthesis. However, a well-known issue of these models is their tendency to replicate or even amplify biases present in their training data. Previous work have seen bias amplification as a fixed, intrinsic feature of the model. As a result, the methods used to tackle this issue, such as attribute guidance or policy solver, require costly retraining or fine-tuning of the model. Moreover, because bias amplification is seen as a feature of the model, the sampling process and its hyperparameters are typically optimized to balance sample quality and computational efficiency, and so far, no one has systematically analyzed how the sampling process itself affects bias amplification. Therefore, we address this gap by asking the following question. Does the choice of sampling hyperparameters influence the level of bias in images generated by diffusion models? Diffusion models generate images by reversing a forward diffusion process, starting from pure Gaussian noise and iteratively denoising the samples. This denoising process can be either deterministic or stochastic. In the latter case, fresh noise is injected during sampling. To investigate whether the level of bias is influenced by the choice of sampling hyperparameters, our method is threefold. First, we define the level of bias as ρ, the probability for a given sample to be bias aligned, meaning that its bias attribute aligns with its target attribute. For instance, if the target attribute is a person's occupation and the bias attribute is its gender, then male lawyers are bias-aligned samples. We then simply check whether ρ of generated images is greater than ρ in the dataset. Our second methodological step is to identify three groups of ubiquitous hyperparameters that are potentially relevant to bias amplification. First, the conditioning strength, with a guidance scale of classifier-free guidance, which controls how close the generated images are to the target class. Second is the computational cost, with the number of sampling steps and type of integration scheme. And third is the amount of stochasticity, that is to say, the variance and time window of the noise injected during sampling. We then assess the impact of those hyperparameters on the level of bias and the image quality, on classical models such as DDPM, and state-of-the-art models such as stable diffusion, on deterministic and stochastic samplers of different kinds, and on datasets exhibiting different types of biases, like multi-column list or Lion 5B. As expected, the experiments show that the guidance strength is positively correlated with the level of bias. We see on this experiment on bias list with ρ equals 90% that for the same model, some hyperparameter settings induce a reduction of bias, while others induce an amplification of bias. Similarly, the number of sampling steps is found to be positively correlated with the level of bias. So, for the same model, increasing the number of sampling steps also increases the level of bias. Moreover, we see that increasing the number of sampling steps also increases the image quality, as expected, but surprisingly, the image quality quickly plateaus while the level of bias goes on increasing. Rather counterintuitively, the amount of noise injected during sampling is also positively correlated with the level of bias. So, for the same model, increasing the variance of noise and enlarging the time window with injected noise also increases the level of bias. We found that a low number of sampling steps correlates with a lower level of bias. Our hypothesis is that numerical errors lead the sampling trajectories away from the bias-aligned modes, effectively leading to reduction of bias. Contrary to what we expected, increasing the stochastic sampling noise leads to an increase in the level of bias. One explanation is that noise effectively corrects for numerical errors by allowing the stochastic sampling process to jump between paths, guiding trajectories towards bias-aligned areas of the image space. Finally, yes, the choice of sampling hyperparameters influences the level of bias in images generated by diffusion models. The results also call for more careful constructions of vanilla baselines when analyzing models or building debiasing methods. Finally, it is in principle possible to design a debiasing strategy by simply tuning the sampling hyperparameters. Thank you for your attention.